All right, folks, today we're going to talk about scale changes, very similarly to the way we talked about translations. Okay, so with this scale change, there's two versions that I'll have you write. The first is the rule, and that allows you to plug in points and find the image under a scale change. And then there's the equation, which starts out in this ugly looking form, but we simplify so it looks traditionally like y equals. Okay? What I want you to do right now is pause the video while you write this information on a note card. Okay? Do include what I put here, and then these three things that I put on a bracket here are only going to be used for the homework. It won't really be used past that for like a quiz or a test. Okay, what's really important though, that when you see this A and B in both this rule and this equation, they are not the same A and B from the purple note card. Okay, so make sure that you get that written down as well. Okay, but pause the video and take care of that for me. All right, I want to talk a little bit about how this works, dealing with the translation that you already know. The rule for a translation was x plus h and y plus k, and that related to our purple note card parent function equation a little bit differently. So I'm going to use the example x plus 2, and then let's do y minus 3. If I use the parent function, the square root of x, if I see an x plus 2 in the rule, I would see an x minus 2 in the equation. Then this minus 3 really means going down 3, so I still want to say minus 3 for the equation. With this rule, what you see is what you get on a graph. If I say plus 2, that means I'm adding 2 to the x value. That pushes it to the right on a graph. Minus 3 on the graph would go down, but we know that on the purple note card it says x minus h in grouping symbols, so we got to switch the sign there from that. What I'm going to show you is actually that between the rule and the equation, both things actually change, the first part and the second. The reason that's actually happening, even though I wrote a minus 3 over to this side, that's only because if I'm thinking about y, it's on this left-hand side of the equation. So if I took a y minus 3 from the equation of my translation rule, and switched it, it would look like y plus 3 in my equation for the parent function. But we know we like equations to look like y equals, and that's why it ended up being minus 3, is because of where it was in the equation. So what we're going to do to talk about the scale change is, you'll notice this says a times x, but over here in the parent function it says divided by a. Same thing goes for this second part, is this was times b, but over here in the equation it was divided by b as long as it was with y. So that's how we're going to attack these scale changes and equations. We're going to just switch the operation and then simplify. So to take a look at the first one, we've got a parent function of y equals x squared. How you'll start these out is just by writing the parent function with a little bit of room. So this is x squared, so I'm going to write some grouping symbols with a squared attached. And then we're going to go ahead and fill something in those parentheses and put something over here with y based on what we see in our scale change rule. All we have to do is switch the operation. What I'm going to encourage you to do here is, if you see a fraction, switching the operation from multiplication division is the same thing as just reciprocating. So if you see a 1/2 times x, okay, that's the same thing as if we switch it to timesing by 2, the reciprocal. So 2x will go inside where it was for the parent function. Similarly, if I see a 1/3 times y here, I'm just going to reciprocate and call it 3y in the equation. But we want all of our parent function equations to be as simplified as possible, so we've got a square on this side and get rid of that 3 on that side. So 3y will just bring down while I fix this side. That 2 gets squared and the x, so that'll look like 4x squared. Then we want to divide by 3 on each side, and we have y equals 4/3 x squared. And then now we have this coefficient in front of x where if we wanted to write purple note card stuff, we could describe this 4/3 as the a value. Okay, so that's it for that one. Over here, same process. We're going to start with y equals. This time my parent function is a cubic, so I'm going to write my parentheses with a third power. But again, all we have to do is reciprocate or switch the operation that we see. So this says 1/5 with the x. So in our equation, we're going to have the reciprocal 5 with the x. Now, something you want to pay attention to is with negatives here, when we're switching the operation, that does not switch the sign at all. So this -4 will go to -1/4. Okay, the sign stays the same. All right, then same process, we're going to simplify on the right here and then move that -1/4. So I'll bring the -1/4 down for the first step, and then just cube 5 and cube x. So 5 cubed is 125, and then x cubed, you just smush it. All right, I never want to divide by a fraction, so instead we're going to multiply by the reciprocal here. We do want to multiply by the negative. That cancels out negative times negative, leaving us with a positive y. And on the other side, we're doing the same thing, multiplying by -4. It is fair game for us to multiply those over because we don't have any order of operations to pay attention to. And then 125 times -4 is -500. Then we tack that x cubed on at the end. And that's it. Now, one parent function that can be a little bit tricky is the square root of x, just because when we take the square root of something, it doesn't always come out nicely, or it may be a situation where we have to rationalize or simplify. So we do have to be careful with something like this. Let's see what happens here. We'll start out with y equals and then a big square root symbol, and then we just have to switch it like we have been doing. This time I'm starting with a 5, so the reciprocal will be a fraction, 1/5. Same thing goes for this 4y. It'll go to 1/4. And here's where kind of we have an issue show up. First thing I'm going to do is just rewrite this as the square root of x over 5. That way I don't have two separate pieces causing me problems under here. But now the issue is this is really equivalent to the square root of x over the square root of 5. And it's fine to have the square root of x underneath a radical since it's in the numerator, but it's not okay to have the square root of 5 since that's what we're dividing by. So what we're going to do is rationalize, and you've done this before by multiplying by the square root of just whatever you see, but I'm going to encourage you to just do this underneath this original radical symbol that we drew. Okay, so just draw a times to the side for me. And what we're kind of thinking here is I need this 5 to be something that comes out nicely, or a perfect square in this case. So I need to multiply by 5 on top and bottom to get that to happen for me. So 1/4 is coming down again, and then I have x times 5 is 5x on top, and then 5 times 5 is 25 on the bottom. And now I can say that that really is the square root of 5x over the square root of 25, which is just 5. Last step, we still want x by y by itself, so we do have to multiply that 4 over. Okay, and you can either put it on top, or I like to move the fraction to the side and call this 4 over 5 times the square root of 5x. Again, the reason I like to do that is so that I can clearly see the a and b values from the purple note card. Okay, because if I have you write a sentence, it will be using those ideas from the purple note card, and this in front would be the a value, and this inside the square root would be the b value. Okay, it's not as easy to see if you put that 4 in the front on top, but if you're not writing a sentence, they are equivalent, so you're okay to write it that way. The next one has a parent function that's exponential, 5 to the x. So again, we want to write out our parent function, but this time x isn't in a grouping symbol, it's just in the exponent. So when we fill it in, we'll have to fill it in up there as the power. We have 3 over 2 in here, so if I reciprocate that, that'll become 2/3 for our power. And then 7y will become 1/7 y. Now, when we solve this, we do have to be careful. Okay, I'm multiplying by 7, and for the quadratic equation, the cubic equation, there's nothing wrong with combining those. But an exponential, we do have to pay attention to order of operations. If we think about order of operations, I have exponents happening and I have multiplication happening. But exponents have to come first. And because there's a variable in my exponent, there is no way to simplify this 5 to the power. So I have to write this 7 just out in front. You cannot combine them. Okay, so make yourself a note here. My parent function had a 5 in it. And so I'm going to have to end up with something with a 5 in it. Okay, has to stay all the way through. If I'm thinking purple note card, this 5 will not be part of my steps. The 7 is my vertical something, and the 2/3 would be my horizontal something. Okay, the 5 is just the base. A hyperbola is another example of where you may have some issues when simplifying. The reason for that is because your x is in the exponent, and if you have to put a fraction down there, a fraction inside of a fraction isn't super nice for us. Okay, so let's see what happens on this one. Y equals, that's on the bottom, so I'm just going to leave that bottom blank. That will go fill in. Now, this scale change looks a little bit different than some of the ones we have been doing. Instead of having a number to the side, it looks like x divided by 5. And that's how I'm going to think about this to switch it. If this says x divided by 5, all I have to do is switch the operation. So the inverse operation of division is multiplication. So I'm going to have to write x times 5, which just looks like 5x. Okay, but it has to be in the denominator. That's where my regular x was. And that's not a problem. Okay, if I did have a 1/5 down here, I'd have to reciprocate to solve. No worries on this one. I see a -4, so over here I'll have a -1/4. Remember, the sign stays the same. And then I just have to go solve. Okay, what I want you to do right now is pause the video to solve for y on this one and complete number 6 for me. And then we'll talk about them here in a couple minutes. So here, when you write it, you could put the -4 on top and write that over 5x, as long as you make sure I see that that x is in the denominator. That's super important. Or you can write it as y equals this -4 out in the front with 1 divided by that 5x, again, x clearly in the denominator. Okay, these are both the same, but again, if we're talking about describing a transformation, sometimes purple note card, it's easier to see A and B when the A is out front. I did tell you with hyperbolas, if there was going to be an A value, it would be shown up on top. If there is a B value, it would be down below, and then a K will be to the side like we've seen on all of our parent functions. Okay, but I don't care how you write it. You will see equations like this, but you're okay to write it like that. Okay, your choice. All right, so hopefully this one went okay for you, because even though it's a cube root, we ended up with the cube root of 9x, and there's nothing wrong with that because the cube root of 9 doesn't break down, and we don't have any fractions to worry about. So our final answer here will be 6 times the cube root of that 9x, since we can't take this 6 and distribute it through that grouping symbol. All right. The next thing we're going to do here is actually go backwards the other direction, and the other direction is actually a little bit easier to work with because you don't have to worry about simplifying like we do with some of those parent functions. Okay, what we do have to worry about, though, is when we're trying to decide what we're switching, you have to make sure something is with y and something is grouped with x to make this work. Okay, but we're writing the scale change rule, okay? With the rule, we're going to start out with S for scale change, and then it'll look like the ordered pair XY. And our job is to write an ordered pair, something with X and something with Y, to fill this in. Okay? If I look at my equation here, they're just letting f of x represent any parent function. A lot of times I won't give you a specific parent function in problems like this, so you don't have to worry about reverse simplifying, working backwards from some weird looking numbers. Okay? So in this basic form, I'm going to look at the x value first. So in this form it says x divided by 3. So just like that one when I was showing you on the equation version, when we're writing the rule, we're just going to think the inverse operation of that as well. So instead of division, we're going to say multiplication, and x times 3 is just 3x. Very similarly, this says y divided by 7, so we're going to say 7 times y in the rule. All right, the next one we're starting the same way, right? S of x comma y equals, and we're supposed to put something with x, something with y based on what we see. Okay, so I'm back to a fraction. Fractions you just have to reciprocate when you see them. So this says 5/6. I have to write 6/5, and then that goes with x. Now you'll notice there is nothing with y. That means there's not a scale change to the y values of your ordered pairs, so you just keep them regular y. Okay, cy, right y. On number 9, something's a little bit different than the previous ones though. This -8 isn't inside with x, but it's also not over with y. So that's our first step, is we have to move some stuff around. When we're looking, the only way something is going to be grouped with x is if it's inside the grouping symbols to start with. So any numbers in front have to go over and be moved to talk about with y. Because this says -8 times f of x, we're going to divide by -8 on both sides. So then I've got y divided by -8 equals f of x. And we have to write the rule from there. So again, s of xy equals, and big ordered pair, something with x, something with y. Because nothing was with x, we just call it x, just like the last one. But here it says y divided by -8, so we want y times -8. Or -8y. All right, I want you to pause the video and take care of number 10 for me. We should have had our rule look like 1/2 x and 6y, just switching both of those things we see. The last two problems here, the only thing that's different is we have 3 separate numbers, and again we have to move some stuff around to put them together. So this 5 in front, remember, cannot move with x, it has to go this way. It's okay for me to divide by 5 on this side, but if I try to divide by 5 on this side, I have a fraction within a fraction, and I never want to see that on your paper. Okay? So instead of dividing by 5, we can multiply by the reciprocal. So that's what we want to do here. The reciprocal is 1/5, and then we can simplify by multiplying straight across. So 1 times y is just y, and then 5 times 2 is 10. So I've got y/10 equals, and then on this side I keep that f of 4x. Okay, from there, our rule would be s of xy equals, we saw 4x, that'll switch to 1/4 x. I see y divided by 10, so that'll be y times 10, or 10y for that. All right. So last one here, pause the video and take care of number 12. When you multiply by that -4, you can do so in a couple ways. You can write that as -4y/3, or you can write it as -4/3 y. Y up top and y to the side are equivalent, so it's entirely your choice how you want to write that, because how we interpret it for the scale change is exactly the same. Okay, our scale change will look like s of xy equals, and because there's a 7x, I'll write 1/7 x. And here, the -4/3 in front or kind of a combination still just reciprocates to -3/4. Now, we've seen some negatives show up, and on your note card you saw a couple rules dealing with negatives. When we see a negative y value, that means I've got a positive version and a negative version. That's a reflection over the x-axis, whereas if I have a positive and a negative x value, that's a reflection over the y. So negatives, just like with purple note card stuff, are going to represent reflections for us. All right, I just want to show you on 13 that there are some parent functions that make our life easy to write the rule. Absolute value is one of those. There's not a lot of simplifying involved with absolute values, so these are ones that we can look at directly and write the scale change rule from them. Okay, so we're going to do that here, just like we have been doing. We're looking with x for the first one. I see a 6x, so I'll write a 16x. And then with the y for the second part, this says y divided by 4, so I'll say y times 4 for the second part, and that's it. Okay, you can be given an actual parent function to do the same process. But the whole idea of the scale change rules is to help us with things like you see on number 14. Okay, the power of using a rule, whether it's a translation rule or a scale change rule, is because we can take any ordered pair on an original graph and plug it into that rule to get the corresponding point on the image. Okay, so that's really helpful for us when we're doing transformations of graphs. So I've given you a graph over here, and they said we're going to call this f of x. So this notation is very similar to what we were doing on those previous problems. There's not a parent function because the shape these points make is not one of our traditional parent functions. Okay, so they're just calling it f of x because it really is a function here, passes the VLT. Okay, but what we're going to do is in a t-table here, we're going to set this up where the left-hand side of our t-table represents our original ordered pairs, so call that x and y. And over on the right-hand side will be our scale change. Okay, so we'll write s of xy equals, and then figure out what our scale change is based on this transformation they gave us. Okay, so here it says 2x, we'll write 1/2 x. And then it says y divided by 3, so we'll say 3y. And because it's a rule, all we're going to do is find our originals and just plug them in, do exactly what it says. This is 1/2 times x, this is 3 times y. Okay? So looking at our picture, let's write down our original ordered pairs. A is -6, 0. B is -2, -1. C is 0, 2. D is 2, -3. And our last one, E, is 6, -3. If you're given a graph and the major points where corners happen, or those vertices, aren't labeled, I do want you to pick letters to assign to those, because when we graph the image, we're going to use those same letters to help guide us to connect the points. So with that in mind, let's go ahead and start out A prime, that notation for an image, B prime, C prime, D prime, and E prime. And all we have to do is go take all of our x values and multiply them by 1/2. Take all of our y values from our ordered pairs and multiply them by 3. I'm going to do x's first. So all of these we're just going to take times 1/2. So -6 times 1/2 is -3. -2 times 1/2 is -1. 0 times 1/2 is 0. 2 times 1/2 is 1. And 6 times 1/2 is 3. So x is done. Then we're going to do the same thing for y. This time it says times 3. So 0 times 3 is 0. -1 times 3 is -3. 2 times 3 is 6. -3 times 3 is -9. So that last one's -9 as well. And there are my image points. on our new graph, we're going to plot those points and label them. Sometimes on a graph, I won't give you a scale because there's no guarantee that these numbers, after scaled, end up small. So you may have to expand your graph to include larger numbers, or sometimes they're really small in decimal values, so you might want to count by something smaller as well. So starting out, -3, 0 gets an A prime. Then -1, -3 is B prime. 0, 6 is C prime. 1, -9, D prime. And 3, -9, E prime. The reason these labels are so important is because when we do a scale change, we want to connect our points in the same order that they were originally connected. Now here, we didn't have any reflection, so it's pretty easy to see that the shape didn't really change. It just kind of got squished and stretched. But sometimes it's reflected over either the x or the y-axis or both, and so it's not as obvious to see. Okay, so we just have to follow in order the letters in the original pattern, so A, B, C, D, E, to connect ours. So A, B, B to C, C to D, and D to E to finish up. Now, I want to talk about those squishes and stretches that I was just talking about. If you look at our original, it looks like from left to right we got smaller. So left to right we call horizontal, and this would be a horizontal compression. Specifically, a compression by a factor of 1/2, because that's what we multiplied everything by. If I look up and down, that's a vertical, and it looks like it got taller, so that'd be a vertical stretch. Specifically, my y value went from 2 to 6, so it stretched by a factor of 3. Rules, what you see is what you get, okay? So now that we know that, working backwards, we are asked to find the scale change that stretches a graph horizontally by a factor of 4 and shrinks it vertically by a factor of 1/5. So let's write out our rule, S of x, y. And remember, horizontally refers to x values, left and right on a graph. And we want the left and right to be stretched by 4. So we just write 4 times x. Stretching, we got to multiply by something larger than 1. Then the next part, vertically, is y, up and down on a graph. And by a factor of 1/5, what you see is what you get. We'll write 1/5 with the y. Last problem here just deals with how I want you to write things. It says the zeros of a function are -12, -4, and 8. Zeros are just your x-intercepts. And I've been trying to convince you that intercepts are ordered pairs. Okay, so I want you to write these as ordered pairs. I went ahead and set this up like a table, kind of like what we did on that previous problem, to represent our original points and our scaled points with the 1/4 x and the -2y that we were given this one. So if they're x-intercepts, that means the y value is 0. So my first one's at -12, second one's at -4, and the third one is at 8. But then it also gave me a lone y-intercept here of 16. So I can say 0, 16 for it. Okay. Functions can have multiple x-intercepts. That's common. We've seen rational functions that do that. But they will only have one y-intercept. Otherwise, it wouldn't pass the VLT. But now that we have those, we just have to plug them in the rule. All the x's multiplied by 1/4. So -3, -1, 2, 0. And then our y values all get multiplied by a -2. So 0, 0, 0, -32. Okay, so you'll see an x-intercept under a scale change is still an x-intercept, okay, because that 0 is not going to be affected by a scale change. Same thing, a y-intercept by a scale change stays the y-intercept, so that won't as well. So our shortcut here is just all the x values, you plug in the x part, all the y values, you plug in the y part, but you do have to write them as ordered pairs for me, okay? If you have any questions while you're working through your homework, please feel free to come see me.